Hey, so in today's video I wanted to talk to you about logarithmic differentiation, and in order to do that I wanted to maybe start a little bit earlier and just talk about the fact that logarithms allow us to express complex complex expressions as simple sums and additions, which was actually something that was used for complicated calculations prior to the development of computation. Some of you might recall the existence of the logarithmic slide, which allowed conversion of products into simple additions. So say if you had an expression something like 1 plus x, all that squared, multiplied by x minus 1, and all that divided by x, and let's say square root of x plus 1. It would be quite difficult actually to find the result of this expression without using some sort of a computational aid. But computational aid wasn't really available before the development of the computers, so people developed logarithms, and let's say that this is my expression for y equals to this. Now I know that I can take logarithm of both sides, natural log even, so ln of y is the same as ln of this whole expression. So that's ln of 1 plus x, all that squared, square root of x minus 1, all that divided by x, root x plus 1. And if I recall our logarithm laws, I can expand this. So whenever we have a product of two terms and taking log of the product turns into addition of two logarithms. So we're going to end up with ln of 1 plus x, that in the bracket all squared, plus ln of, I'm going to turn root x minus 1 into x minus 1 to the power of a half, because that's what square root corresponds to. And then if I have a division, I put a minus in front of it, and again here we have another product, so that will be plus. So ln of x and plus, but we have minus in front of this expression, so it will be minus again, ln of x plus 1, all that to a power of half. Now I can simplify it just a little bit, more by remembering that if there is an index number in the term in the logarithm, that number drops in front of the logarithm. So I'm going to end up with ln, rather 2ln of 1 plus x plus half of ln of x minus 1 and minus ln of x minus half again ln of x plus 1. And actually probably it's probably a little bit easier to notice that finding a result of this is probably a little bit easier if you're dealing with just a computation without computers, let's say, but some hand methods than finding this result. So then I suppose the last step would be to just to find the value of this term in real numbers, would just be to realize that y equals to e to the power of ln y. So we could take this value here, value that comes out from this computation, and put it to our Euler number. But that's not really something that I wanted to talk about, because what I wanted to talk about is differentiating functions like the function that we just dealt with. And differentiation of this function, I suppose, is probably possible, but it will be quite difficult, because note that we have there is a product rule above the line, product rule below the line, and finally we have to use the quotient rule for the full function, which makes it quite complex and difficult. So we have developed a little bit of a shortcut, which is going to help us find the derivative of expression like this one here. Now, dx, derivative of ln of x, is simply 1 over x. Little bit more generally, if I have d over dx by the chain rule of ln of, let's say, some function of x, f of x, that's going to turn into 1 divided by f of x multiplied by d dx f of x. So to find, if I'm taking the derivative of function, of log of a function, I'm going to divide the log of what's the derivative of what's in the log by that function. So, for example, ln, let's see, dx of ln of 3x squared minus 4x and plus 5, by the chain rule, I'm going to turn this into dx of ln u, and I'm going to multiply that by dx, ddu rather here, of 3x squared minus 4x plus 5. So that will turn into, above the line, we're going to end up with 6x minus 4, and below the line, so that's from ddx, and from ddu, ln u is 1 over u, and 1 over u turns into 1 over 3x squared minus 4x plus 5. So more generally, whenever I'm dealing with, again, the dx of ln of y of x, when I'm dealing with a derivative of a function, the result of that derivative is going to be 1 over the function multiplied by the derivative of what's in of the function itself. So ddx 1 over the y of x, which actually turns out to be very helpful for dealing with derivatives of the function, like this function over here, where you have products and so on and so forth. So in order to find the derivative of the function, like the function we just dealt with, the first step is to take the log of the function. Take the log of the function. What that means is that if I have a function, again, I'm going to rewrite this, y of x equals to 1 plus x squared by square root of x minus 1, and below the line I have x by x plus 1. Actually, I'm going to change it into plus 2, just so that it's not simplifiable. So now you can see that I can't simplify this. So now I have to take the log of the function. So ln of y of x is equal to, taking the log of this, keeping the logarithmic laws again in mind, I'm going to end up with 2 ln of 1 plus x from the first term plus half ln of x minus 1 from the second term minus ln of x over here, and minus half of ln of x plus 2. So that is again equal to ln of y of x. This is the natural log of the function that I started with, and this is the function that I want to find the derivative of. Now I have the natural log of that function. Step 2, take a derivative of that natural log. So d over dx of ln of y of x is the same as derivative of every single one of those terms taken separately. So that would be d dx of 2 ln of 1 plus x plus d dx half ln x minus 1 minus d dx ln of x and minus half, I suppose that should be in minus d dx half of ln of x plus 2. So second step, take the derivative of both sides. Now if I take a derivative of those two terms, let's take a look at the right hand side first. So then right hand side, first term is d dx of 2 ln of, in the bracket, 1 plus x, and by the chain rule that is going to turn into 1 over 2 by 1 plus x. Sorry, not 1 but 2 here. So by the chain rule this is going to turn into 2 divided by 1 plus x. The second term is d dx of half ln x minus 1, and that is going to turn into 1 over 2 by x minus 1. Then we're dealing with d dx of ln of x, which is simply 1 over x, and d dx of ln of x plus 2, and actually that's half. Half goes over here, half ln x plus 2, and that is going to turn into 1 over 2 x plus 2. So that's the right hand side, and the left hand side is equal to d dx of ln of y. Now to take a look at the left hand side, we have d dx of ln of y of x, and as I mentioned earlier, that is always going to be equal to 1 over y dy dx. So I'm going to combine those two, what I've gotten over here. So from the left hand side I'm going to get that 1 over y dy dx, and from the right hand side I'm going to get 2 divided by 1 plus x plus 1 divided by 2x minus 1, and plus actually minus 1 over x, and minus 1 over 2x plus 2. So this is the resulting, I combined the two expressions, and here is the key thing. This is what I'm interested in. This is the derivative of the function dy dx. So dy dx is, when I solve for this, dy dx, the derivative of my original function 1 plus x squared square root of x minus 1 divided by x root of x plus 2. So this is the original function that I started with, and I was interested in the derivative of this function. So the derivative of this function dy dx is simply the function multiplied by this expression. Because, like, note that over here I have 1 over the function multiplied by dy dx. dy dx is the derivative I'm interested in. So to solve for dy dx, I multiplied the right hand side of my expression just by the function. So y multiplied by all this, and if I substitute, that's going to turn into 1 plus x, all that squared square root of x minus 1 divided by x square root of x plus 2. And all that has to be multiplied by 2 by 1 plus x plus 1 divided by 2x minus 1, and then minus 1 over x, and then minus 1 over 2x plus 2. Okay, so we arrived. Just let me go over the steps again. So step 1, find the so step 1, take the log of the function. Step 2, take a derivative of the resulting expression. Step 3, remembering that dx equals to ddx of ln y of x equals to 1 over y dy dx to solve for dy dx. And what that means is, okay, and that's where we need to be. So logarithmic differentiation really helps us to find the derivatives of complex expressions without having to escape to difficult and awkward use of product and quotient rules and chain rules as well. And we're going to practice this week and maybe next week, and we'll see how we get on. So thank you for watching. If you have any questions, drop me a line, send me an email, or leave a comment. Thanks for watching, and this is Mr. Ozek. Michael out.